to yet another session of molecular symmetry and group theory. With the last class, you are familiarized with the possible symmetry operations and elements of molecules. And apart from this single operations or elements, there can be multiplication of operations also, or the combinations of operations. And today we are going to discuss about the multiplications or combinations of operations, and also we will discuss more about the point groups and the requirements of point groups. Let us start the topic with the combinations of operations. Let A and B are two operations such that BA is equal to C, then C is the product of A and B. Then BA means apply A first and then B. If BA is equal to AB, then we say that the both operators commute with each other, or the both operations commutes with each other. Let us look with an example. It is the water molecule we are using here, and here in water molecule you know that it have 4 elements of symmetry, or the 4 operations. Which are they? They are E, C2Z, sigma V xz and sigma V dash yz. These are the 4 operations. Any 2 operations of this water molecule commutes with each other. Let us check. Here you can see sigma V xz into C2Z is equal to sigma V dash yz. Here you can see the water molecule, here HA, here HB. Upon acting this C2Z, we get this configuration. The C2Z means rotating in anti-clockwise through the Z axis. It is the angle of rotation is 180 degree. Then what happens? HB goes to the place of HA and vice versa. So this will be the configuration. Now the second operation operating is sigma V xz. So what happens? Sigma V xz is the plane bisecting the molecule. So what happens? Again these hydrogens exchanges. Okay. So this will be the result. And if we do sigma V dash yz alone, then also we will get the same configuration, because sigma V dash yz is the molecular plane itself. Okay. So the both these configurations are similar, or the same result. And you know here this is the C2Z axis about which we are rotating 180 degree in anti-clockwise direction, and here you can see the molecular plane sigma V dash yz. Sigma V dash yz is the molecular plane, which is the plane containing the molecule, and this sigma V xz is the plane bisecting the molecule. Okay. The plane bisecting the molecule. So here this equation we have verified, and the second one, that is, if the order of operations are exchanged, then what happens? Again the same result occurs. Let us check. That is, this operation means we have to apply sigma V xz first. So sigma V xz means it is the plane bisecting the molecule. So what happens? HB goes to the place of HA and vice versa. So this will be the figure. Now secondly we have to operate C2Z. So C2Z is the rotation, okay, 180 degree rotation through the Z axis. So what happens? Again this exchanges, and this will be the result. And it is same as when sigma V dash yz is applied. So sigma V dash yz is the molecular plane which is acted upon this molecule. This is the molecular plane. Then what happens? It will result in the same configuration. That means sigma V dash yz again. So both these operations are commutative, right? So sigma V xz into C2Z is equal to sigma V dash yz. C2Z into sigma V xz also is equal to sigma V dash yz. So what is the inference? Both these operations commutes with each other. And it should be noted that all these 4 operations available for the water molecules commutes with each other on their binary multiplication. Okay. So, the result of combinations of two symmetry operations generally depends upon the order in which they are performed. They do not always commute with each other. Sometimes they commute with each other and sometimes they does not. So, for a non-commutative operations, we have to look an example BF3 molecule. So, what are these non-commutative operations? We have to define them. If the product of two operations A and B depends on the order in which they are performed, so that BA not equal to AB, then the operations are said to be non-commutative. For example, the molecule BF3. In the molecule BF3, the two operations sigma V and C3 do not commute with each other. That means, sigma V into C3 does not equal to C3 into sigma V, right. So, let us do the operations to verify whether it is correct or not. So, first operation we are applying is C3. So, here this is the atom B and 3 fluorines are placed here. So, if C3 is performed, C3 means what? It is the 120 degree rotation. So, 120 degree rotation, the first place fluorine goes to the third place and vice versa. So, first fluorine comes to this position, third one goes to this position and the second one goes to this position. So, this will be the result. Clear? Then what happens? We have to apply sigma V plane. So, this is the plane we are applying. Then what happens? This 3 goes to this place and 2 goes to this place. So, this will be the final configuration, right. Then now we are exchanging the order in which the operations are performed. So, here sigma V is applied first. So, that sigma V is the plane, this plane bisects the molecule. So, that 2 comes here and 1 goes there. So, this will be the configuration. And after that, secondly we are performing C3. So, what happens? 2 goes to the place of 3, 3 goes to the place of 1 and 1 comes to the second position. So, this will be the result. You look the two configurations, they are not similar. So, that we can confirm what? These two operations do not commute with each other. Okay. The next term we are discussing about is inverse of operations. What are inverse operations? For any operation that can be performed on a molecule, there will be another operation which will completely undo what the first operation does to the molecule. So, that is known as the inverse operation. Let A be the operation performed on a molecule, then there exists another operation, that is X, denoted as X here, which will completely undo what the first operation does to the molecule. That is what the A does to the molecule, that exactly nullified by the next operator X. Then we say that X is the inverse of A, X is the inverse of A, or otherwise we can say A is the inverse of X. Okay. So, that X A equal to E is equal to Ax. Thus, here we can substitute in the place of X, we can substitute A inverse, because A inverse of A is X. So, A inverse A is equal to E is equal to A inverse. Okay. So, an operation and its inverse always commutes with each other. So, let us check here. C2 square is equal to E, right. Once C2 is performed on a molecule and then again one more C2 is performed, then what the first C2 does to the molecule is exactly nullified by the second C2. So, we get identity. Okay. So, here we can split these operations. C2 into C2 is equal to E, right. Now, this C2 goes to the other side. So, C2 is equal to E into C2 power minus 1 or C2 inverse. So, C2 is equal to C2 inverse. That means the operation is its own inverse. And here likewise sigma square is equal to E, that is plane applied to the molecule. Again that plane repeats, then that will give to the molecule's original position or the identity. And here sigma is equal to sigma inverse, and also I square is equal to E, again I is equal to I inverse. So an operation is its own inverse. Next we are dealing with the inverse operations for proper rotations. Here you can see C3 cube is equal to E, whether it is right or not. C3 cube is equal to E. C3 cube means what? C3 into C3 into C3. C3 is what? It is the 120 degree rotation in the anti-clockwise direction. So 3 times C3, 120 in plus again 120, that means 240, again 120 means 360 degree. So at C3 it repeats its original configuration. So C3 cube is equal to E. We can split this to C3 square into C3, that means 240 degree rotation again after that 120 degree. So that will result in a E, or we can say C3 square is equal to E into C3 inverse, or we can say C3 square is equal to C3 inverse. Okay, that is 240 degree rotation if done to the molecule, then 120 degree rotation cancels the effect of a 240 degree rotation. So C3 square is equal to C3 power minus 1. So C3 square is the inverse of a C3, or otherwise C3 is the inverse of C3 square, right? So to generalize this, we have to put here in the place of a 3 we can write n. So Cn, what is then 2? 3 minus 2. So it is n minus 1, Cn power n minus 1 into C3, that means Cn is equal to E. So this is the generalized equation for this. And in the case of improper rotations, the inverse operation will be like this, that is Sn power n equal to E for n is equal to E1. So to generalize this, we have to split this up. So Sn power here n minus 1 into Sn is equal to E for n is equal to E1. And if n is equal to odd, then what happens? Here in the place of n, here comes 2n. So Sn power 2n is equal to E for n is equal to odd. And here also we have to generalize. So here we want to split this up. So Sn power 2n minus 1 into Sn is equal to E for n is equal to odd. Now we have discussed about the multiplications or combinations of operations that are possible for the symmetry operations or elements, right? So now we are moving to the group theory. So coming to this group theory, we have to know more about mathematical groups. What are mathematical groups? The collection of mathematical objects known as elements or members which are related to each other according to the rules such as closure rule, associative rule, identity rule and inverse rule. These 4 rules are obeyed by the elements of that group, then only we say that it is a mathematical group. So for point groups, here the elements we are discussing are symmetry operations. So our elements are symmetry operations. So a point group here is defined as the set of all the operations, the action of which leaves one point of the molecule unmoved or invariant. Okay. So one point is invariant or unmoved upon the operation. Okay. The molecule leaves one point invariant upon that operation. So such collection of operations are known as point group, right? So the conditions are for the point groups have to be discussed, and our point group also must satisfy these 4 mathematical rules. Which are they? The closure rule, associative rule, inverse rule and identity rules. Then only we say it as a point group. So, what is closure rule? Closure rule is that the product of any 2 element of the group as well as the square of each element must be an element of the group. That means, if A and B are 2 elements such that AB is equal to C and BA equal to D, then C and D will be the elements of the group, and also their squares also the result of their squares also will be the element of the group, right. So, A square is equal to F and B square equal to G. These are 2 different operations resulting, then these 2 operations will also be the elements of the group. Okay. So, this is the closure rule. So, this must be satisfied by the elements of the point group. The second one is the identity rule, that in each group there will be an identity element which commute with all others and leaves them unchanged, such that A into E is equal to E into A is equal to A. That means, this identity operation does nothing to the molecule and the molecule retains its configuration. Clear? The third one is associative rule, so that the elements should obey the associative law of multiplication. What is the associative law of multiplication? A into BC is equal to AB into C, right. And the fourth one is inverse rule. Each element of the group has an inverse which is also an element of the group, such that x into A is equal to A into x equal to E. Then x is the inverse of A. Okay, x is equal to A inverse. Clear? And for an illustration, we are selecting the molecule water. Here you can see the water molecules C2 Z axis and also the molecular plane, which is the molecular plane, this plane, and the plane bisecting the molecule, that is the sigma V x z. Sigma V x z is the plane bisecting the molecule. So, the first rule we are checking is a closure rule, adherence to closure rule. So, we know that water molecule has 4 symmetry operations such that E, C2Z, sigma V x z and sigma V dash y z. So, the point group is C2V, and here we have to check whether 2 operations result in another operation of the same group. Here sigma V x z into sigma V dash y z will be equal to C2Z. Now, C2Z is also an element of the group, right. So, we have to check whether it is right or not. So, sigma V x z into sigma V dash y z means we have to perform sigma V dash y z first. So, we are performing sigma V dash y z first. Sigma V dash y z means it is the molecular plane. So, it is the molecular plane, this is the plane containing the molecule. So, it does nothing to the molecule and the same configuration repeats. And after that we are operating the second operation, this is the second operation, that is sigma V x z. So, sigma V x z is the plane bisecting the molecule. So, this is the plane. So, again HB goes to the place of HA and vice versa. So, this will be the result, and we have to check whether it is equal to C2Z alone. So, C2Z is operated. So, what is C2Z? It is the axis through this axis we are rotating 180 degree in anti-clockwise direction. So, HB goes to the place of HA and vice versa. So, again this will be the result. So, both results are same, right. So, C2Z is the element of the group. Now, we have to check with the other 2 operations also. We are here selecting C2Z and sigma V x z. Okay. sigma v x z have to be performed first and then C2 z. Okay. Then what is the operation we are getting? It is the other operation other than E. There is only 4 operations available for a water molecule, and if we are multiplying these two, we get the other operation, that means sigma v dash y z, right, other than E. Okay. So, we have to perform this. Sigma v x z is the plane bisecting the molecule. So, what happens? Hb goes to the place of Ha and vice versa, and it is exchanged. So, this is the result, and after that we are performing the second operation, that is C2 z. So, C2 z is the axis through which we are rotating, right, through which we are rotating. So, Ha goes to the place of Hb and vice versa. So, what is the result? The final result will be the like that. So, again we have to check sigma v dash y z. Sigma v dash y z is applied on this molecule, which is the molecular plane. It does nothing to the molecule, same result is obtained. So, again we can say that sigma v dash y z is also the element of the group, right. So, this is the closure rule. The second one is adherence to identity rule. Which is the identity rule? When an element is multiplied with its identity operations, it does nothing to the molecule, it repeats its configuration, original configuration. So, we are taking here C2z, C2z into E is equal to E into C2z is equal to C2z. So, we have to check first. Here we want to apply E first, okay. E have to be performed first. So, upon acting E, it does nothing to the molecule and the same configuration repeats. After that we are doing C2z. So, C2z is the axis through which we are rotating 180 degree. So, again the molecule is twisted and Hb comes first. And in the second case we are performing C2z first. Here we have to perform C2z first, so that the hydrogens are exchanged and Hb comes here, Ha comes here. Okay. After that we have to perform what? E, or the identity operations, so that the molecule again retains its configuration. So, the two configurations are similar, right. It is the result of C2z only. So, the water molecule elements of the water molecule do obey what? Identity rule. The third one is adherence to associative rule. What is the associative rule? A into BC will be equal to AB into C. So, let A is equal to C2z and B is equal to sigma v x z and C equal to sigma v dash y z, which is the molecular plane. Now, we have to perform what? A into BC, right. So, A is what? A is C2z. C2z into BC means what? Sigma v x z into sigma v dash y z, that will be equal to what? AB into C. So, AB is what? C2z into sigma v x z, that into C, that is sigma v dash y z. Now, we know that closure rule, right. So, according to closure rule, sigma v x z into sigma v dash y z will be another element of that group. Okay. So, only one element is there, that is C2z other than E in the case of a water molecule. So, the result of sigma v x z into sigma v dash y z will be what? C2z only, because there is only 4 operations and one is identity operation and these 3 operations are available. Okay. So, sigma v x z into sigma v dash y z will be the other operation, that is C2z, and here also C2z into sigma v x z will be equal to the other operation in that group, that that is sigma v dash yz, right. So, we can substitute here, this equation will change to C2z into what is the result of this C2z. So, we are writing C2z. Then here also the result of these operations will be what? Sigma v dash yz. So, sigma v dash yz into again sigma v dash yz. Okay. So, the operations are repeated twice, so that it will be equal to identity, right. So, the elements of the group obeys what? Associative rule. So, we can check whether it is right or not. This is the water molecule. We have to first apply this operation, that means sigma v xz into sigma v dash yz. That means it is C2z, right. According to closure rule, the result will be the other operation. Okay. So, this operation when performed on this molecule, this is the axis through which the molecule is rotated at a 180 degree, then what will be the result? The hydrogens are exchanged. So, this will be the result. After that, we have to apply the C2z. So, after C2z, again these hydrogens are exchanged and this will be the result, right. And now, we have to perform this operation. From these operations, which has to be performed first? This one has to be performed first. So, sigma v dash yz have to be performed, which is the molecular plane, the plane containing the molecule, which does nothing to the molecule, and the repetition of the configuration occurs, right. And after that, we have to perform this operation. The result of this operation is what? It is the other operation of the group, that is sigma v dash yz, which is the molecular plane. Again the molecular plane acted upon, we will get the same configuration, right. So, the both operations are both these operations gives same result. That means the four elements of the water molecules obeys associative rule. The fourth one is adherence to inverse rule. So, an operation in the set is an inverse of itself. That means, one operation is performed, again that repeats, that will result E, that means identity. Okay. So, here we are taking sigma v xz, which is the plane bisecting the molecule. Here we have to perform sigma v dash y, sigma v xz, so that the molecule is bisected by this plane, so that HB goes to the place of HA and vice versa. This will be the result. Again sigma v xz, then again what happens? Here plane comes and HB goes to its real position, and the result will be like this. Okay. So, that is what exact result of the operation identity, right. So, this rule also is satisfied by the four elements of a water molecule. So, the four elements of the water molecule do belong to a point group. Now, another thing we have to discuss is about finite and infinite groups. From the name itself, you can understand what it means. Finite group means it contains limited number of elements. That is, for example, E, A1, A2, A3, etc. up to AH. There is a limit AH. Okay. So, for this examples are C2V, C3V, etc. point groups. Okay. So, example, the C2V point group we already know, that is water molecule. It contains 4 elements, only 4 elements. So, its elements are limited, right. So, it is a finite group. Likewise, C3V also. So, this molecular point group also is containing limited number of elements. So, it is also an finite group. The 4 elements of a C2V are E, C2Z, sigma V xz and sigma V dash yz. And in the case of a C3V, it contains 6 elements such as E, C3, C3 square, sigma V dash and sigma V double dash. So, the order of groups are named here as 4 and 6. What does it mean? The C2V contain 4 elements. So, it is known as the group having order 4. And in the case of a C3V, it contains 6 elements, so that its order is 6. And while considering this infinite group, we can say it contains unlimited number of elements, infinite number of elements. So, that its elements can be written as E, A1, A2, A3 etc. up to A infinity. There is no limit. The examples of such groups are C infinity V and D infinity H, which are mostly shown by linear molecules. Okay. Next point we have to discuss is about abelian and non-abelian groups. Abelian group means a group in which all the elements commutes with each other. For example, C2V point group. In C2V point group, any two operations commutes with each other. Okay. So, that type of a group is known as abelian group. That means all its elements, if any two elements are multiplied, that multiplication is commutative, right. And these 4 operations are available for the C2V. Out of the 4 elements, the multiplication is always commutative for any two pair. And while in non-abelian groups, the multiplication is non-commutative for some pair of elements. For some pairs, it can commute, but all pairs do not commute with each other. Then that group is known as non-abelian groups. For example, C3V point group shown by ammonia molecule. It contains the 6 elements, but we have checked with this C3 and sigma V previously, right. So, the C3 and sigma V do not commute with each other. So, since they are not commute with each other, it is falls under the group non-abelian, right. With that, we have come to the end of the session, and today we have discussed about the combinations of operations or the multiplications of operations. Also, we have discussed about the rules that have to be satisfied by the elements of symmetry or the symmetry operations to form a point group, and also we discussed about the finite and infinite groups as well as the abelian and non-abelian groups. And in the next class, we will learn about the point group classifications, that is how the molecules are classified to different point groups. Let us wind up for today. Thank you.